rice inspires a new class of smart materials. In advanced materials engineering, innovation is usually associated with high-performance alloys, polymers, and semiconductor systems. However, new research from the University of Birmingham, published in Matter, suggests that a common pantry staple may offer an alternative path to adaptive design. When packed into dense granular assemblies, ordinary rice demonstrates a rare mechanical behavior that challenges conventional engineering assumptions. The material exhibits what researchers describe as rate softening. Under slow, sustained compression, packed rice maintains structural strength. When compressed rapidly, it weakens. This contrasts with most solid materials, which typically stiffen or strengthen under high loading rates. For product designers and engineers, this counterintuitive response presents a practical opportunity. Structures that adapt automatically to how quickly they are stressed without relying on sensors, embedded electronics, or software. From granular complexity to predictable performance. Granular materials such as sand, grains, and industrial powders are widely used across sectors including agriculture, pharmaceuticals, mining, and construction. They are often treated as difficult to model and control because their behavior depends on shifting internal interactions between individual particles. The Birmingham research reframes this variability as a controllable design feature rather than a limitation. At the center of the discovery is friction. In densely packed rice, internal networks of contact forces, often referred to as force chains, carry mechanical stress through the structure. During slow loading, these frictional connections remain stable and supportive. When stress is applied quickly, friction between grains drops significantly. The internal force networks reorganize, and the structure loses strength. By pairing rice with other granular materials that demonstrate the opposite behavior, becoming stronger under rapid loading, the researchers created composite metamaterials with tunable responses. Through careful selection of material combinations and structural geometry, engineers can design systems that bend, buckle, stiffen, or soften depending solely on loading speed. The resulting mechanical behavior is embedded directly into the architecture of the material, eliminating the need for external control mechanisms. Applications in robotics, protection, and industrial systems. The implications are particularly relevant for soft robotics, where designers seek to balance flexibility, safety, and load-bearing capability. Conventional robotic systems depend on rigid components and complex control frameworks to manage varying forces. A speed-sensitive granular metamaterial offers a different approach. Components could remain compliant during slow, deliberate movements while responding differently under sudden dynamic loads, improving adaptability without increasing system complexity. Protective equipment also represents a viable application area. Materials that remain flexible and comfortable during regular use, but alter their mechanical response under impact, could help reconcile two traditionally competing design priorities: wearability and energy absorption. Similar principles may apply to packaging systems, industrial safety equipment, and transportation components that must respond differently to gradual stresses versus sudden shocks. More broadly, the research supports a growing interest in what can be described as passive mechanical intelligence. Instead of adding layers of digital control to static materials, engineers can design structures whose behavior emerges from internal physical interactions. For sectors focused on durability, cost control, and operational reliability, this approach reduces dependency on electronic components and may improve performance in extreme or electronic-sensitive environments. Rice is unlikely to displace conventional structural materials in mainstream applications. However, this work illustrates how overlooked materials can inform new engineering strategies. By treating granular physics as a programmable asset, designers can create systems that adjust in real time based purely on how forces are applied, expanding the toolkit for adaptive and resilient product development.